Assalamu alaikum everyone. This is course EE-212 and this is the last lecture of the resonance circuits. Till this point we have covered the Bode plot series and parallel resonance circuit. Then we have already studied about the scaling of electrical circuits. Now in this lecture we will be moving on towards the filters, and this is actually the application of the resonance circuits. So basically there are two types of filters. The first one is passive filters, and the second type is active filters. So the passive filters are the ones that are made up of passive elements, and the passive elements are resistor, capacitor and inductor, and more specifically they are the ones that do not generate any power. They can store or release energy, but they are not generating any power. So the passive elements are resistor, capacitor and inductor. Then the second type is active filters, and the active filters are made up of transistors and operational amplifiers. Transistors and op-amps. So in this lecture we will only be covering the passive filters. So there are four different types. The first one is low pass filter. So if I have to show it by a graph, it actually just allows the circuit or the gain values to pass through the filter if the frequency value is less than the cutoff frequency. So this is the cutoff frequency. So if the frequency values of the signal are less than omega c, then it will allow it to pass through the filter. But if it is greater than the omega c value, then it will just filter it out. Then the second is high pass filter. So it is just opposite to the low pass filter, so it will allow the, if I have to draw it on another graph, it will allow the signal values having the frequency greater than the cutoff frequency, but before that it will just filter out the gain values before the cutoff frequency. Then the third one is band pass filter, and the last one is band reject filter. So for band pass filter we have two different frequencies. The first one is lower cutoff frequency and the second one is higher cutoff frequency. There is a center frequency omega naught at which the gain value is maximum, and before the lower cutoff frequency there is no signal that is passing through the filter, and after the cutoff frequency there is no signal that is passing through the circuit. And for the band reject filter, again we have two frequencies, lower and upper cutoff frequencies, but it will allow the frequencies, the signal with frequencies lower than the lower cutoff frequency and the frequency values greater than the higher cutoff frequencies. So all the signal values that are within the bandwidth of omega L and omega H, that will not have any output and it will be filtered out. So this is the band reject filter. This is the band pass filter, low pass filter and high pass filter. So I will be starting from the low pass filter. So the circuit diagram of low pass filter consists of a resistor and a capacitor. So this is a series combination of resistor and capacitor. There is a voltage Vi, that is the input voltage, and we are getting the output across the capacitor. To show it graphically, it is actually giving you the output values or the gain values at the output if the frequency is less than the cutoff frequency, but after the cutoff frequency the signal will be filtered out, so there will be no output after the cutoff frequency. So the circuit consists of a series combination of resistor and capacitor. There is an input voltage Vi and we are getting the output voltage across the capacitor. Now if I have to find the voltage gain, that will be V0 over Vi. So the voltage gain would be 1 over j omega c over R plus 1 over j omega c. So this is your capacitive reactance and this is your whole impedance of the network. So now if I'll simplify that, so the voltage gain will become V0 over Vi. It is actually equal to 1 over 1 plus j R omega c. So this is your gain equation. So now if you look at this particular transfer function, this represents a simple pole. So there is no polynomial, nothing in the numerator, so there is no zero in the transfer function. We only have a simple pole that is a polynomial in the denominator. So if I have to represent a voltage gain of the low pass filter, it is actually a simple pole. Now what we have to do, we have to find the break frequency or the cutoff frequency. We know that the low pass filter gain graph with the changing frequency value, we have a certain frequency omega c, which is a break frequency or cutoff frequency. We have to find this omega c. Now if we have to find this omega c, we already know that the half power frequencies these half power frequencies will occur at 1 over under root 2 times the gain magnitude. So I have explained it in the previous lectures. So the half power frequency actually occurs at 1 over under root 2 times the gain value, and if I have to find the gain magnitude, so this is your gain equation, and if I have to find the magnitude of this equation, that will be V0 over Vi magnitude and 1 over 1 plus j R omega c magnitude. So this value will become 1 over under root 2 because we are going to find the cutoff frequency. So for cutoff frequency, the gain will be 1 over under root 2 times the gain value at which the maximum power was occurring. So 1 over 2 is replaced by V0 over Vi, which is the gain magnitude, and the other side of the equality, it will become 1 over 1 plus omega RC square whole under root, and after solving it will become 1 over 2 is equal to 1 over 1 plus omega RC square and 1 plus omega RC square is equal to 2, and after solving it will give you 1 omega is equal to 1 over RC. So this is your cutoff frequency or half power frequency. So this frequency is actually depending on the values of resistor and capacitor. So if you have to change this cutoff frequency for the low pass filter, you just have to vary the resistor and capacitor value, and then you can change the frequency values that you can allow to pass through the filter. So this was your cutoff frequency. So now if I have to draw the gain characteristic of the low pass filter, So we already know that gain is actually equal to 1 over 1 plus j omega RC, and now if I have to write this one in standard form, so that will become 1 over 1 plus j omega over 1 by RC. So this is your frequency axis and this is your gain, right? And this is your 0 dB, 20, minus 20, and this is your cutoff frequency. So this value is 1 by RC, and we know that for simple pole, the magnitude graph is actually 0 till cutoff frequency, and after cutoff frequency it will start decaying at minus 20 dB per decade, right? So before the corner frequency, which is controlled by the values of resistor and capacitor, there is a low frequency asymptote, this one. So this is a straight line. So till 1 over RC it is equal to 0 dB, and after 1 over RC it will start decaying at the slope of minus 20 dB per decade. So it shows that for the frequency values less than omega c, which is the cutoff frequency, the gain is actually equal to 1, and after that, after omega c, the gain will start decaying, and by 1 we mean that it is actually 0 dB. So it is log 10 1 is actually equal to 0 dB. So at this point the gain is actually equal to 1, which is the maximum value. So before the cutoff frequency the gain is actually equal to 1, and after the cutoff frequency it will start decaying. So if I have to draw the low pass filter characteristic again, so it is the ideal characteristic, but if I have to draw the realistic characteristic or the actual one, so it will be something like that. So it will be crossing the ideal characteristic at the value 1 over under root 2 times the gain value, which is the half power frequency, because at omega c this is the cutoff frequency or the half power frequency, so the gain value will be 1 over under root 2, and then it will be decaying. So this is the real characteristic of the low pass filter. So now if you have to design the low pass filter, you just have to change the value of resistor and capacitor for the specific cutoff or half power frequencies, and it actually is just a series combination of a resistor and capacitor, and you are taking the output across the capacitor. So this is a low pass filter. For the high pass filter, the characteristic is like this. We have a cutoff frequency, and before the cutoff frequency we actually don't have any gain value. The gain is actually equal to 0, but after the cutoff frequency the gain is equal to 1. So this is again the ideal characteristic, and if I have to draw the real characteristic, this will be something like that. We have 1 over under root 2 times gain value at the cutoff frequency. So this is the point where the realistic curve actually crosses the ideal characteristic. For the high pass filter, the ideal characteristic just shows you that there is no signal before the cutoff frequency, but in real circuits we have some gain value before the cutoff frequency as well, but the value is quite low. So now if I have to draw the circuit for this particular high pass filter, it is again a series combination of resistor and capacitor, but now we are taking the output across the resistor. And now if I have to write the gain function for this high pass filter, it will be V0 over Vi, and numerator we have resistor, and in denominator the impedance will be R plus 1 over j omega C, and after solving G j omega, that will be j omega RC 1 plus j omega RC. So now in this transfer function we have 1 0 and specifically 0 at origin, and then we have a simple pole. So now if I have to write that in standard form, the gain function will become j omega over 1 by RC and 1 plus j omega over 1 by RC. So now if I have to find the cutoff frequency from this graph, that will be omega C is equal to 1 by RC. That is similar to the low pass filter, in which we found omega C is equal to 1 by RC, and in the standard form it is actually j omega over A or j omega over omega C. So this is your cutoff frequency. So in the denominator we have 1 over RC, so the cutoff frequency is actually equal to 1 over RC. So now if I have to draw the frequency characteristic again, the Bode plots, so the gain curve, if I have to draw that, I will start here. So what we have a 0 at origin. So 0 at origin, it has a slope of plus 20 dB per decade. So it is actually passing through the frequency axis at 1 by RC. So this is a 0 at origin. For 0 at origin, it will be this line, and the slope of this line is 20 dB per decade, and this represent j omega over 1 by RC. Now for the pole, it will have a value that is 0 till the corner frequency or the cutoff frequency, and after that it will start decaying at minus 20 dB per decade, right? And this particular curve is for 1 plus j omega over 1 by RC. So now if I have to draw the composite, that will be following the simple 0 till 1 by RC. Before omega C or before 1 by RC, the simple pole value is 0, so it will just be following the 0 at origin curve, and after that it is 20 dB and this is minus 20 dB, so it will become 0 dB. So after 1 by RC, it will be a straight line. So this is your composite graph, and this point is 0 dB. Again, if it is 0 dB, so the gain value is actually equal to 1, because this value is log 10 of 1. So this represents a high pass filter. So if I have to draw again, the high pass filter is allowing all the frequency values that are greater than the cutoff frequency, and before that it is actually in ideal case giving you no output, or the gain value is actually equal to 0 before the cutoff frequency. But in the ideal case, at the cutoff frequency we have the gain value that is 1 by under root 2 times the gain at which the maximum power occurs, right? So this is your real characteristic and this is your ideal characteristic. So this was your high pass filter. Now moving on towards the band pass filter. So I have already covered this band pass filter when I was talking about the series resonance circuit. In the series resonance circuit, we have actually an inductor, capacitor and resistor. So I have started from this particular circuit in which we have a series combination of inductor, capacitor and resistor, and I was taking the output across the resistor, and we have an input voltage Vi. So in that particular part of the lecture I have defined all the terms of bandwidth, cutoff frequencies, and quality factor. So these are the terms that I have already talked about in the start of the series resonance circuit. I will be just giving you an overview what we have talked about. So now if I have to just draw the graph of the bandpass filter, so it is actually giving you the gain values or giving you a particular output between two frequencies. One is omega low and the other is omega high. Then we have a center frequency, which is the resonant frequency at which the gain value is maximum. So at this point the gain value is maximum, and then we have two cutoff frequencies, a lower cutoff frequency and the higher cutoff frequency, and the bandwidth is actually just the subtraction of lower cutoff frequency from the higher cutoff frequency, and this is your ideal characteristic of the bandpass filter. And for the realistic characteristic it is actually this curve. So at the cutoff frequencies the gain value is actually 1 over under root 2 times the gain value at which the maximum power occurs, right? So this is your bandpass filter. Now if I have to just give you an overview what we have done in the series resonance circuit when I was defining the bandpass filter, we started from again the voltage gain equation. So V naught over Vi is the voltage gain, and I find out that R plus omega L minus 1 over omega C, that is your voltage gain equation. So now if I have to simplify it, that will be Gj omega is actually equal to 1 over 1 plus J omega L over R minus 1 over omega C R. So this is your transfer function. So now if I have to find the half power frequencies, I have to take the magnitude of the gain curve, and after solving or taking the magnitude of the gain, I find out that the final equation, that was plus minus R is equal to omega L minus 1 over omega C. So the magnitude of the transfer function actually give me the equation, that is plus minus R is equal to omega L minus 1 over omega C, and from this particular equation we can find the lower and upper cutoff frequencies, and we have two different scenarios. One is for omega less than omega naught and the other one is for omega greater than omega naught. For omega less than omega naught we have XL less than XC. So if XL is less than XC, it means omega L is less than 1 over omega C, right? So from the equation A, so omega L is less than 1 over omega C, it means that the resistance value is negative. Similarly, for the values of frequencies omega greater than omega naught, the resistance value will be positive because XL is greater than XC. So if first term is greater than the second term, so the whole term will be positive. So omega L will be greater than 1 over omega C and the resistance value will be positive. So these are the two equations that we will get from equation A, and after solving equation 1, that is equation 1 and this is equation 2. So now if I will be solving equation 1, so it will become omega square LC minus 1 plus omega RC is equal to 0, and after further solving omega square, I am taking LC common, it will be plus omega r over L minus 1 over LC. It is equal to 0. So after solving this quadratic equation by using the quadratic formula, which is omega is equal to minus b plus minus under root b square minus 4ac over 2a, I got the value for omega low, that is equal to minus r over 2l plus minus r over 2l square plus 1 over LC. So this was your lower cutoff frequency, because this equation is actually for omega less than omega naught. So that's why the frequency value that I got is the lower cutoff frequency. After solving the equation number 2, we will get the higher cutoff frequency, that is r over 2l plus under root r over 2l square plus 1 over LC. So in this way we had already calculated these two frequencies, the lower cutoff frequency and the higher cutoff frequency. So after that we found out the bandwidth equation, that is actually equal to the higher cutoff frequency minus lower cutoff frequency, and by using the equations for the higher cutoff frequency and the lower cutoff frequency, we found out that the bandwidth is actually equal to the ratio of resistance and inductance of the circuit. So this defines the bandwidth. So if you have to change the bandwidth of the bandpass filter, you just have to change the values of resistor and inductor. So this was your bandpass filter, and in the bandpass filter it is a series combination of inductor, capacitor and resistor. We are getting the output across the resistor, and if you have to find the cutoff frequencies, you can use the formulas that we derive for the low cutoff frequency and the higher cutoff frequency. These formulas are actually in the form of circuit elements. We only have resistor, inductor and capacitor. In the start of the series resonant circuit lecture, we have also derived another formula which was in terms of quality factor and the resonant frequency. So if you have to change the bandwidth of the bandpass filter, this is the bandwidth, the frequency values for which we have some gain value. This defines the bandwidth. So if you have to change this, you just have to change the values of resistor and inductor. So this was your band pass filter. So in band reject filter, again we have a series combination of resistor, capacitor and inductor. We have an input voltage Vi, R, C and L, but now we are taking the output across the capacitor and inductor. So this will be your output voltage. And if I have to draw the graph for that band reject filter, so it will not have any output for the frequency values that are between the omega low and omega high frequencies. So before lower cutoff frequency we will have gain equal to 1, and after higher cutoff frequency we will have gain equal to 1. Again, this is the ideal characteristic. Now if I have to draw the realistic curve, that will again start decreasing from the peak value, and it will cross the ideal characteristic, or it will have the lower cutoff frequency at 1 over under root 2 times the gain value, and it will be 0 at omega naught, which is the center frequency. And then after omega naught it will again start increasing, and it will cross the ideal characteristic, or it will have the higher cutoff frequency. At this point the value of gain at lower cutoff frequency and the higher cutoff frequency will be 1 over under root 2 times the gain value at which the maximum power occurs. So this is the band reject filter. So in this lecture we have covered 4 different type of filters. So we started from the low pass filter, in which we have a series combination of resistor and capacitor, and we found out the voltage gain equation for that, and then we also calculated the break frequency or the cutoff frequency, after which there will be no signal value that is passing through the filter. Actually the filter filters out all the frequency values that are greater than the cutoff frequency. So the cutoff frequency was actually equal to 1 over RC. In the high pass filter, again we have a RC circuit in which we are getting the output voltage across the resistor, and if you have to set the cutoff frequency, you just have to change the values of resistor and capacitor. Then I have defined the band pass filter, it is the series combination of inductors, capacitors and resistance. We are actually getting the output across the resistor, and then we derive the formulas for the lower and upper cutoff frequencies, and also to set the bandwidth we calculate the formula that is dependent on the resistance and inductance value. So in the band reject filter, it is actually again the series combination of R, C and L, but in this case we are getting the output voltage across the capacitance and inductance. Now we will be solving a few examples related to the filters. So in the first example, we are given a RC circuit in which the output is taken across the capacitor. A resistance of 10 kilo ohm is attached in series with the capacitance of value 20 microfarad. There is a source voltage Vs, and it is asked to sketch the magnitude characteristic of the RC circuit. Now if you remember in the lecture when I was talking about low pass filter and high pass filter, whenever we are taking the output voltage across the capacitor in the RC circuit, it is actually a low pass filter, and if the output is taken across the resistor, then it is a high pass filter. So now if I have to sketch the magnitude characteristic, first I have to calculate the transfer function for the gain, and gain is actually equal to V0 over Vs. So first I have to find the output voltage, and if I have to calculate the output voltage across the capacitor, I have to apply the voltage division, and V0 will be 1 over j omega c over R plus j 1 by j omega c into Vs, right? So I will take this Vs to the other side of the equality. So V0 over Vs is equal to 1 over j omega c over R plus 1 over j omega c, and after solving it will become 1 over 1 plus j omega RC. We know the value of resistance and we also know the value of capacitance, so it will become 1 over 1 plus j omega. The resistance value is 10k and the capacitance value is 20 microfarad. So after solving, the gain equation will become, the gain transfer function will become 1 over 1 plus 0.2 j omega. So in the transfer function we only have one simple pole. There is nothing in the numerator, so we don't have any zeros. We only have one polynomial in the denominator, and the term in the denominator is a pole. So this is a simple pole. So now if I have to draw this gain curve, if I have to sketch this gain curve, first I have to convert the pole into standard form, and to convert it into standard form I will write it V0 over Vs is actually equal to 1 over 1 plus j omega over 1 divided by 0.2 is equal to 1 over 1 plus j omega by 5. So the cutoff frequency here is 5. So now if I have to draw the magnitude characteristics, so this is your frequency axis, and at frequency axis till 5, the magnitude will be equal to 0 dB, and after 5 it will start decaying at minus 20 dB per decade. So by drawing the magnitude characteristic of the RC circuit, if the voltage is taken across the capacitor, output voltage is taken across the capacitor, then it is a low pass filter. So this filter will only allow the signals that have frequency less than 5 to pass through it. After that it will start filtering out the signals. So this is the gain characteristics of the simple RC circuit that is given in the example. Now for the second example, example number 2, we are given a RLC circuit. It is a series RLC circuit, and we are taking output across the resistor, and the value of resistance is 1 kilo ohm, the capacitor's value is 1 microfarad, and the inductor's value is 1 Henry. The input voltage is Vs. Now again we have to draw the magnitude characteristics. So first we will find the gain of this particular circuit, and for gain I have to calculate V0 over Vs. This is the voltage gain, and to calculate V0 over Vs, again the resistor will be in the numerator and the equivalent impedance will be in the denominator, R over R plus j omega L plus 1 over j omega C, right? So by just looking at the circuit, we can again assume that this is a band pass filter. Because if in an RLC circuit we are taking the output voltage across the resistor, it is a band pass filter, and if we are taking the output across the combination of inductor and capacitor, then it is a band reject filter. So this is a band pass filter. So V0 over Vs is equal to R over R plus j omega L plus 1 over j omega C, and after simplifying, V0 over Vs will become j omega RC over j omega RC plus j square omega square LC plus 1. Further simplifying, j omega RC over j omega square LC plus j omega RC plus 1. So now we know the values of resistance, capacitance and inductor. After putting the values in the fraction, the value will become j omega 1 into 10 raised to 3 into 1 into 10 raised to minus 6 over j omega square into 1 into 1 into 10 raised to minus 6 plus j omega into 1 into 10 raised to 3 into 1 into 10 raised to minus 6 plus 1. So after solving, it will become 1 into 10 raised to 3 j omega over j omega by 1 into 10 raised to 3 whole square plus 1 into 10 raised to minus 3 j omega plus 1. So this is your transfer function. So now if you look at this transfer function, we have three different terms. The first one is constant, which is equal to 1 into 10 raised to 3. The second one is 0 at origin, and the last one is quadratic pole, right? So now if I have to draw or sketch the magnitude characteristics, first I will write down the transfer function again. It is actually equal to 1 into 10 raised to 3 j omega over 1 into 10 raised to 3 whole square plus 1 into 10 raised to minus 3 j omega plus 1, right? So now we have one constant, one 0 at origin and one quadratic pole. So first, to deal with the constant, it will be equal to 20 log the value of constant 10 raised to minus 3, right? So this is minus 3. The value here is minus 3 and this is minus 3. So now this minus 3 will come before log and it will become minus 60 log 10. This is equal to 1. So for the constant, the gain value will be minus 60 dB, right? So now for the 0 at origin, the standard form is j omega over a, and here it is j omega. It means that j omega over 1. So the frequency at which the 0 will cross the 0 dB line is 1, right? Omega is equal to 1, or a is equal to 1. So I will write a1 is equal to 1. Now for the quadratic pole, a2 will be equal to 1000, because this term is the value of frequency at which two asymptotes will cross each other. Before this frequency, the gain value is actually equal to 0 dB, and after this frequency, the gain value will start decaying at the slope of minus 40 dB per decade. So that was how we draw the magnitude characteristic of a quadratic pole. So now if I have to draw the magnitude characteristic, so I will take it as a frequency axis. This is your gain axis. I will take this as 0 dB, and I will start with minus 20 dB, minus 40, minus 60, minus 80, and then I will draw the line for the 0 dB value. Here it will be 0.1, 1, 10, 100, 1000, 10,000. So this is your frequency axis. So now for the constant value, it will be a constant value minus 60 dB. So this is your minus 60 dB for all the values of frequency. For 0 at origin, it will cross the 0 dB line at 1. So the 1 value is this point, and before and after it has a slope of plus 20 dB, right? So it will be this straight line, this which is crossing the 0 dB line at 1. This is your 20 dB per decade line. Now if I have to draw the quadratic pole, it will be 0 till 1000. Till this point it will have a 0 value, and after 1000 it will start decaying at minus 40 dB per decade, right? So this is minus 40 dB per decade, right? So from this point to this point, this is 1 decade, because 1000 to 10,000, and from 0 it has decayed till minus 40 dB in 1 decade. But in the case of 0 at origin, it was increasing at 20 dB per decade. So from 1 to 10 it has only increased 20 dB. So now if I have to draw the composite line, so I will change the color. So first I will start at this point. So we have 3 different graphs. The first one is 0, the second one has the value minus 20 dB, and the third one has the value minus 60 dB, right? So at this point it's minus 20 dB, minus 60 dB, and 0 dB. So it will become minus 80 dB. Then we will calculate at this point. At this point, both the curves, for the 0 from the origin and for the quadratic pole, both are 0, and for the constant value it is 60. Line will start passing from here. At this point it is 20, 0 dB, and minus 60. So plus 20 minus 60, it will be minus 40, so it will start increasing in this direction, right? So it will go till 1000, right? But after 1000, the slope of the quadratic pole, it is minus 40 dB per decade, but the slope of the zero at origin is plus 20 dB, so it will start decaying at minus 20 dB, right? Minus 20 dB per decade. So this is, so if this is not included in the graph, so it will start decaying at minus 20 dB. So this is minus 20 dB per decade. So we have a composite curve in which we added all three curves, which is this one. So this is the composite curve for the gain transfer function that we calculated for the series RLC circuit, in which the output was taken across the resistor. But we also know that this is a band pass filter, right? So in the band pass filter, actually we have the lower cutoff frequency as well as the higher cutoff frequency, and between those cutoff frequency the gain value is actually constant, right? So if I have to calculate the cutoff frequencies for the band pass filter, we know the formula for the lower cutoff frequency. It is equal to omega L R over 2L plus under root R over 2L square plus 1 over LC. We know the values of all the elements. It will become minus 1 into 10 raised to 3 over 2 into 1 plus 1 into 10 raised to 3 over 2 square plus 1 over 1 into 10 raised to minus 6, right? So after solving, we will get the lower cutoff frequency value equal to 618 radian per second. Similarly, for the higher cutoff frequency, it is equal to R over 2L plus under root R over 2L square plus 1 over LC. So after putting the values of the element, I will get the higher cutoff frequency equal to 1618 radian per second. So now we have two frequencies. The lower cutoff frequency is 618. It will be somewhere here, 618, and the higher cutoff frequency is 1618, right? So from this point till this point we have a straight line, right? For the band pass filter, we have a constant gain between the lower and upper cutoff frequency. So before and after the lower cutoff frequency and the higher cutoff frequency, we have a slope of minus 20 dB per decade, and between these two frequencies we are getting a constant gain value. So this was the second example in which we have drawn the magnitude characteristic of a series RLC circuit in which the output was taken across the resistor. But now if you have to sketch it for the output value which is taken across the inductor and capacitor values, then it will be a band reject filter. In this case it was a band pass filter. So this is the end of the last lecture on the resonant circuits, and after this point Sir Khanwali, he will be taking over and he will be giving lectures on Laplace, Fourier series and Fourier transform. So if you have any questions till this point, you can ask it on Microsoft Teams. Thank you.